I'm LaRoche Pinel. I'm a researcher working in the Department of Viticulture and Enology at the California State University, Fresno, under the supervision of Luca Briante. And in the lab, we work on different projects in precision viticulture using remote sensing. And one of the oldest projects we are working on is disease detection. We worked on leaf roll detection and red blotch detection, where I'm going to focus my talk today. And we use hyperspectral images. And today, I'm going to show you some results we got using drone-mounted hyperspectral images for red blotch detection. So what is red blotch? Red blotch is a virus that affects the vine that can decrease the quality and in the end also decrease the quantity of the quality of the harvest and the quantity of the harvest. The main point of the disease is there is no curative solution. Once the vine is infected, the only solution is to actually remove it to limit the spread. So there is a question on how we can increase the efficiency of the detection. And we know that actually disease affect biochemical and biophysical property of plants. For example, with our eyes, when we see a red leaf in the vineyard, we know something is wrong. There is a disease, or we know something is wrong. That's already remote sensing that we are doing with our perspective, with our eyes. But using remote sensing, we can go way more than that. So the project started in 2019. We first started to try to understand the science, the theory behind that. So we started in control condition in the lab, and we got really good results to detect red blotch and leaf roll. And we were even able to make the distinction between the vine that were infected by leaf roll or the vine that were infected by red blotch. And we have a publication regarding this step of the project. Then we went in the vineyard, because our objective in the lab is always to work in commercial vineyard and to go toward operational service. So we always, when we work in a vineyard, we always work in a commercial vineyard. So we put the exact same camera, and we took picture of the side of the canopy, and again, here we got up to 90% accuracy to detect red blotch. So the next step to go towards something operational was to put the camera on a drone. So we flew the drone as approximately 30 meters above the ground, so it's like 200 feet, I think. But the question, what is hyperspectral? Because I'm talking about hyperspectral is fabulous, but what is it actually? I know a lot of people are, most of the time, a little confused about what is it. So just to make it really simple, usually an image, you have RGB, red, green, blue. In our camera, in our phone, that's what we have, and we make a composite, and we got an image like this one. Then we have multispectral, where we still have pretty large band, but we have more wavelengths. We can have wavelengths in the near infrared. We can have more color, I will say. So we can see a little more detail, but the bands are still pretty large. Hyperspectral, when we talk about hyperspectral, we have 100 of bands. So that means 100 of images that are really specific wavelengths, so really narrow bands. This way, we can actually target some really specific chemical compound, for example. So when I talk about, that's a spectra of a vine. So that's the amount of light here, the amount of light that is reflected by the vine in the different wavelengths. So in different color in the visible, in the near infrared, and later in the shortwave infrared. So just some information. With our eyes, as I said, we can access some information about chemical, actually. We have information about chlorophyll compound. Chlorophyll actually absorb the light in the blue and in the red and reflect in the green. When there is a lot of chlorophyll in a plant, the plant is healthy, the plant is green. We see that. then we have more information actually in the near that we cannot actually see with our eyes, but with specific camera, multispectral or hyperspectral, you have access to this information. So in the near, you're gonna have information about cell structure. So the reflectance you have here is gonna be affected, is gonna have more or less reflectance according to the cell structure. Then you have also different bands that are reacted to the water content of the plants, and some specific leaf biochemical like cellulose or sugar. For this specific project right now, we are focusing on the visible and the near infrared because we know that disease affect pigment content and also cell structure. So what we did, we went in a commercial vineyard, we sampled like almost 300 plants for PCR analysis, so it's pretty much like COVID. We do PCR to identify the virus, to see if there is the DNA of the virus or no. And that's the truth. That's our ground truth that we're going to try to predict. We are not based on the visual assessment. We're really trying to predict the ground truth, the PCR result. And then, as I said, we flew the drone. We have the images. Thanks to the resolution of about 2 centimeters, we are actually allowed to remove the soil, the shade, so we actually just extract the canopy signal. We also ask, how it is right now. Usually an expert go in the field, or the growers, or the technicians gonna go in the field, is gonna assess if there is any issue, if there is any disease, is gonna try to identify which disease it is. So we also ask an expert to go in this field to do his prediction, to compare with actually the model that we are trying to develop, to see if we are as accurate as the expert, more accurate. For sure we are faster, but those faster means more accurate, not always. So here is just an illustration of the vineyard we went. So we have roughly 264 samples. We have pretty much 50-50 vines that were infected according to the PCR analysis and non-infected. As I say, we have a spatial resolution of 2 centimeters. And here is the average signature of the vines that are non-infected in green. Here, the line in green, that's the average. And the dotted line in red is the average of infected vine. So right now, you see something really clear. The healthy vines are on average more greenish, and the vines that are infected are on average more reddish. And we have also a difference here in the near and in the red edge. But if you look at the standard deviation, that's not that clear. The difference is not as clear as that. So that's why we actually go with machine learning and AI model, because the signal is way more complicated than that. Thanks to this signal, to the hyperspectral signature, we can also predict pigment content of the different vines that we sample. So we predict the green pigment, the chlorophyll pigment. And we noted that with our prediction, we have roughly more chlorophyll in the vines that are non-infected than in the vines that are infected by red blotch. The carotenoid, which is a yellow-orange pigment, the same. We have an estimated concentration that is higher in the vines that are non-infected. And the anthocyanin, that is the red pigment that is produced by the plants in response to an attack to a pathogen. For example, we can see that clearly the predicted anthocyanin is way higher in the vines that are infected. You're going to be like, yeah, that's what we expected. But here, it's really important in our lab, actually. We really try to see if our data makes sense. That's OK, that's obvious, that's what we were supposed to find. But the question was how we will be able to actually see that. And yes, the answer is yes. What we see, what we predict based on the spectra makes totally sense with the literature. So we know that our data set makes sense. Then we took this information, the pigment concentration, as a predictor to be able to predict the infection. And we had an accuracy on the test set of 91.4%. Then, for people who know a little bit remote sensing, we also try an index, like, you know, there is NDVI, for example, that is an index really well known to detect vegetation, usually, and how healthy is the vegetation. That's an index that is really specific to anthocyanin, and using this index, so that means only two bands, the green and the red edge, we achieve an accuracy of 75.4% overall accuracy. Then, when we use a subset of the spectral band that we acquire, so 20 bands, we achieve a model an accuracy of 87% overall accuracy. Now, if we compare with the experts, that's actually higher. So it's way faster to scan a vineyard with a drone, but also the model that we developed here is more accurate than the expert accuracy. And that's explained really well. The expert only sees the visible, and as we saw, there is some information in the near, actually, that the camera can see that an expert cannot, especially when a vine is pre-symptomatic, for example, doesn't show visible symptom yet. And if we look a little more into detail between the expert prediction and our model prediction. So here is confusion matrix, how we read that. In green is what is well predicted. So 92% of the vines that were non-infected according to the PCR well predicted as non-infected by the experts. 76% of the vines that were infected according to PCR were well predicted by the expert as infected. Now, if we look at the error, because that's what we are interested in, right? What's the error? Here, what we call false positive, it's like here we have a slightly higher positive with the model. What that means is like we have a slightly higher risk to flag vines that are healthy as infected. With the model, we have a higher risk of that. It's only a 2% difference, though, than the experts. But the risk that is really important for growers when we talk with them is the false negative. Here, growers have, there is 24% that vine that were infected that the expert missed and flagged as non-infected. This rate is actually as low as 17% when we talk about the model. So we have less risk than to miss infected vines that potentially can spread the virus even more. So now, what are the challenges here with this model? So first, you're going to tell me, yeah, that's one vineyard. You're totally right, and if you think about that, I think you are in the right way. Because when we talk about precision viticulture, AI, if someone comes to you and says, oh, look, I have something, 90%, 100% accuracy, it's perfect, they want to sell it to you, ask question, how it was validating, how many samples there is, how many vineyards, at what time. So here, what we are trying to do is we are building a robust data set. So this data was from 2021. We are adding data from last year and this year in different vineyards with also different variety. Here we were on Cabernet Sauvignon, where the symptoms show really well, that are really expressed. We went in vineyard with different variety, different red variety that have symptoms that are different. And we also went to vineyard with white variety, where it's way more difficult for growers or experts to see anything. So we are building this robust data set to be sure that actually the model is going to be robust enough to go toward a commercial service, actually. So there is also, yeah, the validation of the model, how the model was validated in time, in space. That's really important. And then we have also some thought about the symptoms. If you know a little bit red blotch, the symptoms start from the bottom of the plant. So if you just go with a drone, which is pretty much on the top, we fly a little bit like diagonal, so we see a little bit the side. But here we are also working with a robot, actually, to go in the vineyard, to scan the vineyard, to scan the side of the vineyard. And there is also the question of, yeah, a drone is fantastic. It's super fun. A lot of people are attracted to drone. But for an operational service, how much can you fly with a drone? How long it takes to actually scan a vineyard? How many battery do you need? That's something, if you want to scan, I don't know, the whole vineyard of the whole Central Valley, and everyone is going to want to fly at the same time, you know. So that's a question, like, how can you go toward operational service? Do you need multiple drones, maybe? Do you need to rent them? Like, there is a lot of question behind that to be able to go toward the commercial service. And we are actually working with Grapevine, they were talking about it, to actually go toward that, toward something that is going to be operational and commercial, and that we can commercialize. And the economic model, as I said, here, we use hyperspectral camera where we have a lot of wavelengths, but the goal behind that is to actually identify the specific wavelengths that makes the most sense for the model. Here we have 20 bands, so we already reduced that to be able to build a sensor that is cheaper than actual hyperspectral camera. I'm going to go really fast because I think I ran out of time. So as I said, this year and last year, we acquire more data in different conditions on leafhole and red blotch. We have a robot now also to scan the vineyards. And I want to thank all the partners and the funding, CDFA, F3, ARI, the USDA, UCNR, and also Mark Fuchs from Cornell that do the PCR analysis for us. And thank the whole team I'm working with. That's really, without them, there is no way we could sample and acquire all this data. If you work in precision viticulture, you know acquiring all this data takes time. So thank you to the team, and thank you for your attention. Thank you. I don't know if we have time for questions. Not sure. Okay, I think they have the...
So the data you've collected, is it going to be in the public domain? Who owns the data at this point?
So the data from the tripod, yes, it's going to be in public domain, and we already have some people that ask for it. So if you want it, you can, we can give it to you. And the data from the drone, the raw data, the raw acquisition data, yes, we always share that. So if you want, you can scan it, or we can talk later. And yeah, we're going to share that because we also are publishing all of this work. We just don't publish, obviously, the specific band that we're going to use for our model because we are going through a patent. So we don't publish those specific bands that we're going to work with, but the raw data, yes.
Right here? Oh, wait, sorry. Since you're measuring reflectance, how sensitive were any of the models to ambient lighting conditions? Do you have to train against different conditions? Do you correct for it, calibrate? How does that work?
So that's a good question. I didn't go through all the methodology we went through because I didn't have time, but we actually used a standard reflections panel on the ground. So that answers your question. This way we always have a base for that.
Hi, so I think you might have touched on this a couple times, and I apologize if I just completely missed it, but did the data in the test set come from the same vineyard plot as the data in the training set? And if so, has it been validated to, you know, generalize beyond a single plot?
Yeah, so that's a good question, and I love questions like that. So we did, here we have only one vineyard, so yeah, obviously right now. What I present right now has been. But we did a 5-fold cross-validation here. But that's also why we are acquiring more and more data. This year I'm actually like working on it right now to analyze 3 other vineyards with Merlot. We have Merlot, Cabernet Sauvignon, and other. And this way, the goal is to actually, do like time, also prediction, block out, this type of stuff. Yeah, vineyards out. And we are actually publishing a paper that's going to be available soon about that, about specific validation in precision viticulture, because that's a big topic, I think. Right now, we saw like We see a lot of super good models. They have 100% accuracy. It has been validated on one date on one model, on one vineyard. It's like, you cannot publish that. Like, you have, or at least you have to be honest. Like, yeah, right now we have one vineyard.
Have you looked at how effective this is with asymptomatic positive vines?
So we did with the tripod images, where we have 2 years of data. On the 2 years, we went from June to September every month. So we have the evolution. And the paper is going to be able really soon, before the end of the year, actually, about that. But yeah, that's really interesting because I don't have the figure right now. But we see that the pre-symptomatic, where we don't see anything, the difference that I show you in the spectra, it's only in the near. We see a difference, but only in the near.
You may have already mentioned it. Who were the experts and how many? For your comparison? For your comparison with the drone data, you compared with the experts, right? So who were considered experts?
Yeah, so the expert was actually Mark Fuchs, a pathologist from Cornell that was part of the team that discovered red blotch. So we think that we have actually a pretty good expert on that. And we have, I have to mention also, we had another expert, especially for the tripod data, that was Monica Cooper from UCANR, that she also went in the vineyard to do the prediction. Okay. Thank you. Thank you, Hal.
All right, well, good morning, everyone. Thank you for sticking around, listening to me talk about a little bit about the work we've been doing with robots up in Canada. My name is Geoff Farintosh. I'm a research technician at the University of Guelph, and I work at a research center about a half-hour north of Toronto in the Holland Marsh. This was an area that was drained around 100 years ago, and we're left with this really nice, dark, high organic matter soil. This soil, we mainly grow a few crops that grow really well. Carrots are one of them. Onions are another, and then weeds also grow a little too well for our liking. This is a trial that kind of got out of hand. We were in here hand weeding, we were applying herbicides, but even still, in these low acreage crops, we don't have as many herbicide options. As a result, we see more resistance. Then we have to go in and hand weed. It can be hard to get teams in depending on the time of year or regulations. A lot of problems, and for solutions, some people are starting to turn to robots. Here at the event today, you're going to see all kinds of new designs, and we're really trying to figure out what ones are going to be the winners and what are going to be best for us. I like to talk about how the car industry back in 1908, there were 253 different automotive manufacturers, but just over 20 years later, in 1929, there were only 44 left, and of those, 3 of them are making 80% of the cars. I don't think robots are going to be quite the same, but we really are trying to go through and find which ones are going to work for us. We started this work in 2022. We had LaChèvre from Nexus Robotics. This one has little arms that come down and mechanically pick the weeds. This was more of a development project. It wasn't really quite ready for the fields yet. And then we had the Dino from Naia Robotics. This robot did what it said it would do, but it was kind of limited. It could only kind of carry a small tooling platform, and farmers needed more adaptability. Naia listened to this, and they came back with the Oreo. This robot is what they call an autonomous tool carrying platform. It has a 3-point hitch, so you can kind of put whatever on it that you want. It's loaded with RTK, fully electric, 4-wheel drive. It moves along at a decent clip, about 3.5 kilometers an hour, weighs about as much as a car, and is very adaptable. So we started really, really simple. We don't have GPS in our tractors, so we just put a stake on it, and we're going up and down the fields, making straight lines. It made it nice to follow behind, transplant our onions. This picture, I just kind of had it running one pass ahead of me so I could plant seed carrots behind it. After that, we put a cultivator on it and started sending it through. To help the cultivator stay on the row, we installed this little camera-guided hitch system. This is made by Till and Haig. Basically, from what I understand, you tell it the color of the crop and kind of roughly what your spacing in the row is going to be, and then it'll move the hitch back and forth to kind of match the row. We found this worked pretty well in a variety of different settings, but we still had to do more with the robot. So we kind of fabricated a spray system. We have 2 tanks at the front, both around 55 gallons each, and then a twin boom setup. So the one boom sprays directly on top of the crop. Here we were just kind of playing around early in the season, putting some water on carrots, trying to get them to come up. But then later in the season, we also had a bit of a band sprayer, so we could also spray with the second boom in between the rows. These are just some kind of Home Depot buckets we had. The idea being you can spray something like a non-selective herbicide, kill all the weeds without hurting your crop, and then at the same time we could spray whatever we want in the crop. This year we kind of improved them a bit. We 3D printed out some of our own band hoods that could be rotated, and it was working really well. To kind of control this, we just had a Raven system. So this would make sure we were putting on the rate that we wanted, and also if something happened with the robot, it would shut down the system. So before long, our very bare bones robot was getting filled up with all kinds of screens, and this robot ended up being a great tool for us. This past year, we had trials both on that organic muck soil and on mineral soil, both looking at carrots and beets, and we were comparing it to a tractor. It kind of worked from after seeding right until harvest, where only the robot or the tractor would be in the respective treatments. I don't have all those results to share today. They look a little behind on the robot. It's not quite up to par yet, but I think we know what mistakes we made, and next year I'm excited to address them, and we're gonna go at it again. We're also gonna do some more with the robot. We're playing around with a wick weeder. This is a very early prototype. And then we also wanna do the seeding with the robot as well. So we're gonna have some, these are electric vacuum seeders. So we're gonna be doing carrots, beets, and also onions. So this robot's very adaptable. It's kind of up to you what you make of it. But the other robot that we played around with isn't quite as adaptable. This robot is focused on 2 things right now, mainly seeding and weeding. This is the Farm Droid FD20. And as this robot goes along, it'll drop the seed and it geotags it. So it essentially kind of remembers where that seed is. And then when it comes back later, it can weed around that seed. This robot's much slower, around 0.6 miles per hour. And this is a result of it being solar powered. So you lose speed, but you kind of gain runtime. We were told that this robot would run for around 17 hours at a time. But in our experience, sometimes we were able to run it kind of 24 hours right through the day and get a couple days at a time before we got some cloudy weather and had to slow down for a bit. The first thing we did with this robot was go out and we tried seeding some onions. And we were a little disappointed. To get the density of onions that we wanted, we found we could only seed at around 200 meters an hour, which is kind of a quarter of that top speed. That was a little disappointing. While it still worked well, the problem is if growers have hundreds of acres, they can't have a robot that's going to take a month to seed kind of the designated area or have to buy a ton of them to try to make up for that. So we tried playing around with a few different seeding methods. This is kind of just a very simple diagram of how it works. You can see the seeding disc there I'll focus on. And then from there, it picks up the seed, drops it down that seed pipe, and then there's that valve that kind of lets the seed fall through. So we used that system at first that kind of came with the robot. That's on the left there, just a single row, 3.4 centimeters between the seeds. In the middle there's the conventional system. They actually plant a double row, so 4 double rows of 5 centimeters apart. And this is kind of what we're trying to match here. So to get that, we had to increase the amount of seeds we could put through. On the right, we decided to try taking the same seeding disc in the single row, but just drill in a bunch more holes. So instead of 5, we had 15. And instead of 3.4 centimeters, we said, okay, drop them every 12 centimeters. But we didn't tell the robot that we had drilled all these holes. So instead, it was dropping seeds in a cluster of 3. We weren't sure how this was going to work, but it's kind of similar to how they do transplants. They'll often have 3 seeds in a cell. So we gave it a shot. When the onions came up that first year, it still had to make up a lot compared to the conventional. We were a little disappointed that our stand wasn't a bit better, but we were pleasantly surprised when it came to yield. In that organic soil, the onions can kind of push around and fill out the space. So same thing on the left, you can see the single row. The middle, the conventional. These onions, we may have even had the rate a little too high. They kind of got squished. And in the triple row, even though there were very few onions, they really filled up the space. So our final yield numbers actually being same across the board. There were no significant differences in total yields. Instead, we actually saw significant differences in the percentage of large onions that were seeded by the robot compared to the conventional system. For our first year working with growers, this onion was sent out to do 7 acres in a grower field. We decided to play it slow and safe. We hadn't seen those results yet, so this was just planting in a single row. It crawled along at just over 200 meters an hour, but it did do a great job, and after around 3.5 days, it finished those 7 acres. This year we went back to that same grower, and we wanted to increase that speed. So up from 200 meters an hour, we tried 3D printing our own seeding discs to kind of improve upon that triple cluster idea. And with these discs, I'll just show you some of the speeds here. We were able to triple the speed and actually get better standard results across the board. We played with the valve or not valve, but really promising work. I think we can further improve it, and we're getting to the point where it's starting to make sense for the growers. The grower that we're working with says he wants the robot to hit around 10 acres a day, and the way it is now, we're almost at that number, which is really exciting. These are our yield numbers from this year's trial. Everything's kind of getting a bit more dialed in. We weren't really seeing any differences across the board, which is a good thing. You're not losing out on any yield by using these robots. This is in the grower. These numbers are a little skewed. You can see the robot on the left had really good yield, actually better yield than the seeded trial that he had done conventionally. But there's a big asterisk here that it was a completely different variety. The transplant on the right is the same variety as the robot, but these also had a huge head start. They were started in a greenhouse and put in the field a few weeks earlier. On the weeding side of things, this robot comes with these little wire weeders. They did a pretty good job at removing the weeds, but they'd start to get caught on them over time, and then it would even push soil onto the onion crop. And when this was small, this could cause some issues. So this year we had these knives kind of custom built, and they did a much better job at killing the weeds and not pushing the soil, but again, there's still some work to do, and we were kind of thinking about just replacing the whole tooling bar to really get a weeding system that works well. I should say, because of the density of these onions, we also aren't using the active weeding functions. These are just passively moving through the field. The final issue we kind of ran into with this robot is once the onion crop starts to get big, it would start causing issues. One of the big problems was there's this third wheel right in the middle, which would start going over the leaves. Luckily, FarmDroid is now offering a kit where you can switch to 4 wheels up front, and we're starting to get a bit more use out of it if we can have it in the field running for that much longer. So just some future work. With the FarmDroid, we want to improve that weeding tooling system, and I think for next year we're hoping to hit the grower's goal of seeding 10 acres per day. That's per unit, so if he has 5 units out there and sending them off, you can do his 250 acres in the week, hopefully. With the Oreo, we're going to be using it to seed those onions, carrots, beets. We're going to continue working on the wick weeder and some other implements. And it's also going to start to kind of challenge the FarmDroid. I think we're going to bring it out to the same grower and start seeding some onions as well. It goes much faster, but we're going to see if it can match the same kind of precision and quality that the FarmDroid provides. We have some other trials going on. We're working with Picetta. We're working a little bit with Eco-Robotics now, seeing what it can do. And I'm excited to share some of that work in the future as well. And with that, I just want to thank all people who made this happen, Haggerty AgRobotics, AMAFRA, all of our students at the station. And if I have time, I will open up to some questions. Thank you very much for your time.
Yeah, hello. So I have a question about the off-road data set. So like, did you find or create your own data set to train the model this robot used, or you have any way to do it? Thank you.
So you're asking how we modeled the data?
No, so how did you get the off-road data in the field, or yes?
The offload data?
Yeah, the data in the field. So
like the yield data, or just in general?
Yes.
The different trials?
Yeah.
Just kind of the same method we've been using for a while. For yield, we're taking yield samples out there, double samples, everything's just kind of converted to field scale. Emergence, we're out there counting with clickers how many onions are coming up. I think more of the challenge has been comparing it to a tractor now. It's kind of new for us, having to compare things like labor, maintenance, charge time, and all of that. So we're still kind of working with that right now, but yeah, a lot of data to manage and figure out what it means to help calculate ROI and seeing when these options really become useful to growers. All right, if there are no more questions, I'll let the next speaker go ahead. Thank you for your time.
Good morning, everybody. I'm not Kioumars Ghamkar, I'm his colleague, Cameron Craigie. Kioumars couldn't make it today, so I got the short straw. I'm still on a different time zone, so I'm a little bit tired. But we'll get into this. So I'm here today from a company called AgResearch, which is a New Zealand government-owned agricultural research institute. We're based in the South Island, outside of a city called Christchurch, but we have campuses across the country. I'm a scientist in my own right, and I also am a member of the tech transfer team. And today I'm talking to you in that capacity, representing a technology that Kioumars and the team have developed called MAP and ZAP. And MAP and ZAP is all about a sustainable weed or identification and control system. So the problem that we're addressing with the MAP and ZAP technology is the global herbicide market was massive. There's a pushback on the use of chemicals and a move towards more sustainable modes of managing and controlling weeds. I think both from a production and a consumer side, there's a clear problem here to reduce the burden of weeds on horticulture and crop production. There's also a need to produce more with less in terms of meeting global or feeding a growing global population. We need to be able to increase production quite drastically in order to do that, and weeds representing the one of the highest potential yield reduction or losses to crops. So definitely a problem that we want to solve. So just to take this to a more California related context, we're in a highly regulated state. Organic or current organic weed control strategies can be quite expensive. There's diseases and vines and other things that we've heard about already, some of. Herbicide resistance is a problem. I guess the bottom line here is that the cost of production is high, and there are increasing constraints around doing that in a sustainable way. So the solution that we've come up with is a high-speed, non-chemical based detection and control system that is based around a high-speed identification of weeds using a camera technology at the 2 to 3 leaf stage, and then feeding that information into a laser system which burns out the crown of the weed at that small stage. The key part of our technology is that it's small and modular and designed to be retrofitted on existing or even new vehicle technology. So we're not a robotics company at all. We're looking at solutions that would integrate with other technology platforms. So MAP and ZAP, as you heard, is a camera and laser technology, hence the mapping and the zapping. It is based around the development of a weed library and an integration of AI technology and lasers in order to link the laser and the library via models. It's all about precision application and using data to make good decisions on farm. So with the lasers that we're using currently, we're getting a 90% plus kill rate. We're able to do that without leaving any chemicals in the soil. And we're able to protect the soil microbiome, so we're not tilling the soil or anything like that. So how does MAP and ZAP differ itself, or what is our system? How is it different? So probably one of the key things about it is the ability to access or go under canopies and into less accessible areas where, you know, larger systems on 3-point linkages might struggle perhaps to fit. I guess the other point about it is adaptable, and we have the ability to set it up for monocropping as well as multi-cropping, because we can differentiate green on green. As I mentioned before, we're also system agnostic in terms of what you would mount this technology to, and perhaps as a result of being smaller and more modular, perhaps more affordable. So our data moat, I guess, is a key part of where we're at in terms of developing that weed library, and we're able to quickly add new weeds to that using similar chemometrics techniques that we heard from the first speaker today. So the business model of this technology, so it's an integrated map and zap system. We see the customer of this being via contractors or larger farming operations who would deliver the services of the technology to farmers. The team, as I mentioned, I'm the pretend Kioumars today, and we have, so Kioumars is a plant geneticist, plant phenomics and agri-tech. Jingli Liu is a machine learning expert, and she's developed a lot of the AI and modeling techniques behind this and integrated the sensors and the AI. And myself, I'm in the commercialization team, so I know a little bit about this technology, but a little bit enough to be dangerous with it, perhaps. So the next phase for us is basically trying to raise some capital to get this thing out of our institute and into the real world. We're looking to raise 1.1 million USD to spend out over an 18-month runway, where we're looking to increase the speed of the system, develop markets for it, and stack units on a boom to cover more area. So expansion into the hort and veg sector is also a key part of that. Thank you. I'll leave it at that. I should say, if you're around over the next few days, come and see us in Exhibition Zone 1 at stand 42, and you might get some better answers to questions that you might have than from me today. So thank you.
Just a quick question about the modularity of the system, which I think is an interesting approach for something like this. I'm thinking about like other like laser weighting things I've seen with like rather large laser systems. Like, what's the approximate size and weight of a laser unit? Is it integrated in each cell?
So the current system it weighs around 17 kilos, and it's on a linear actuator as opposed to, so it can move in at 500 mil either way. So yeah, 17 kilos, but we foresee that getting lighter as we develop up the technology a bit more.
Thanks.
Could you make some comments about how your technology is better than UVC-based technologies that provide the same kind of weed killing results?
I'm not familiar with the UVC stuff. Most of my experience with that is around sanitation stuff. So in terms of what we're doing, it's basically just burning out the crown of the weed. So I guess, yeah, I can't say. And I think probably more relevant would, or differentiation would be around the weed library and the way that we train it. Yeah, so the integration of the systems.
Okay.
Just a quick technical, what's your cycle time? How fast you can process these images to actually activate a weed removal technology?
That's a really good question. So at the moment, our system's running at about 0.5 hectares an hour over a 500 mil, I guess, row. We see that getting up to 2 hectares an hour per single unit. So I can't really convert that into cycle time. I'm just thinking it's pretty much real time. So yeah, I don't know the exact seconds in cycle time. All good? Thank you.